Hello everyone, I am Shouvick Mondal from IT Madras, India. This is a joint work with Denini Silva and Professor Marcelo from Federal University of Pernambuco, Brazil. So today's talk is focused on software evolution and regression testing. As per the diagram, we see that the bigger rectangles are different versions of the software, which are results of the evolution of the older version, that is the V0. V0 is changed to V1 in terms of addition of a new code. So addition here occurs in the form of a green square. V1 is changed to V2, where there is a modification in terms of blue square. Green square shows the addition and deletion is shown by the red square. So regression testing is testing software changes for regression bugs, and the efficiency of regression testing is important. The existing solutions in this space are regression test selection, where only the test cases impacted by the changes are executed. Regression test prioritization, test cases maximizing a criteria, that is the criteria of fault detection, are executed prior to those that are not capable of revealing faults earlier. And the third is test suite reduction. Complementary to these three approaches is test execution parallelization, which is less explored in academia but is relevant to the industry. However, there are two issues in test parallelization. The first one is test dependency and the second one is data races. Now, these two give rise to what we call as test flakiness. So we have a test class, a Java class, and it consists of two fields, field 1 and field 2, and there are four test methods. For the first case of test dependency, we see that test method 1 is reading from field 2 and test method 2 is writing to that field. However, we want that the read must take place after the write is complete. So there is a read after write dependency, and this is shown as the dependency T1 arrow T2. However, in parallelization, if these two test cases execute in parallel, this dependency might not be preserved. This gives rise to test flakiness, in which case either test case 1 or test case 2 fails. The second is data race. Test method 3 and test method 4 writing to field 1, and we intend that test method 3 is executed before test 4. So there is a dependency T4 arrow T3. So if we execute these test cases, that is the test methods in parallel without respecting the dependencies, at each run we see that the verdicts can be different. The remedy is to first perform a topological ordering based on the dependency graph of the test case dependencies. And two topological orderings for this case is T2, T1, T3, T4, or T3, T4, T2, T1 in that sequence. So a topological sort would help reveal a safe execution sequence that respects the dependencies. But prerequisite is a test dependency detection. So to gauge the performance of a test dependency detector, we took the state-of-the-art tool, Predict. Predict consists of three steps. The first is to sequentially execute the test cases to record the original order of execution of the test cases. The second step is the dynamic data flow analysis. Dependencies between test cases, between and across test cases are determined, and the dependency graph is constructed. The graph consists of a lot of vertices and edges, so we need to refine the dependency graph to keep only the dependencies that are essential. Essential dependencies are those which, if not respected, test cases that are bound by the dependency relation, if executed out of order, will have their test verdicts toggled. So the overhead of Pradet was substantially larger than the sequential execution itself. So this solution of test dependency detection was not practical. So we developed PASTE. PASTE stands for Parallel Sequential Test Execution, and it consists of three steps. In first step, what you do is we parallelly execute the test cases. So we have this build tool Maven and JUnit as the test framework, and we have four different parameters that are in the pom.xml configuration file for the Maven build. So first parameter is fork count. Fork count is 1c, that is one times the number of cores. That is how many processes we want to fork. So one JVM is assigned to one process. Each process runs on its own core, and one test class is then executed on each JVM. Now, reuse forks equal to true means when we want new process, instead of forking that, we use existing resources that we have already spawned. Then we have the parallel parameter, which can be either method level parallelism, class level parallelism, or classes methods level parallelism. Then there is the thread count parameter. Then we have test cases failing in stage 1 because we have not respected the dependencies. We execute these test cases and dependency is not respected. Some test cases may fail. What you do is you sequentially re-execute these failed test cases in stage 2. For the test class in our example, this step will handle the flakiness through sequential execution of test cases to circumvent data races. So we did not respect the dependency T4 arrow T3. So if we execute this sequentially on the sorting based on the test method names, test method 3 will be executed earlier and then test method 4. So this dependency would be respected and this would circumvent the data race. However, test case 1 and 2, something also failed because they were also executed in parallel without respecting the dependency. So they will continue to fail. Track the test class name. So here is the test class. In the next step, we sequentially execute the test classes. So here we have only one test class and we execute the test class again sequentially. However, the order in which they're executed is the order in which the dependency is respected. So 2 is executed before 1. That was followed in the sequential execution. Now this is the intuition of PASTE and it builds on the observation that broken test dependencies that are manifested in parallel runs involve test cases from the same test class. So a sound parallel approach is one where the test cases are executed in parallel and the verdicts that we get out of it are exactly similar to the verdicts that we get out of a sequential execution. So on one end of the spectrum, we have a sound and slow approach as Pradet did. And on the other hand, we have an unsound analysis, which is very fast, where we have uncontrolled parallelism. And that is just the example we saw. However, we also showed that in PASTE, we have 2 extra stages to circumvent the flakiness. So where the PASTE is soundy, I mean to say that PASTE does not provide the soundness guarantee, but it is reasonable enough to yield end-to-end parallelization. So the one end is at the beginning of stage 1 and the next end is at the end of stage 3. So at the end of, so end to end at the end of the 3 stages, we do have some acceleration. So in the experimental setup, we used a hardware of 8 CPUs. So 4 cores, physical cores with 2 threads per core. We use 25 Java projects from GitHub that use Maven to make sure that the test cases are failing in the parallelization perspective are due to parallelization itself and not due to a non-determinism in the sequential setting. We ran each test suite 10 times, eliminated those test cases that had those defaulting behavior due to non-determinism in the sequential setting. The first research question is it feasible to use parallelization options provided by the build system out of the box to run the test suite? Now, if the answer is yes, PASTE was not necessary. So in 44% of the projects that we studied, no parallel configurations enabled a clean execution. So searching for the parallel configuration for a clean execution is infeasible in general. So PASTE is needed. The second question is it practical to use a test dependency analyzer to partition test sets so as to enable sound parallelization? We already saw that the answer is no, because Pradet, which we used as the state of the art, the cost of it was substantially higher than the cost of the sequential execution itself. How reliable is PASTE? So this is from the effectiveness perspective. PASTE was effective enough to circumvent test flakiness provoked by parallelization, and we did not find any test cases failing at the end of the third stage. We observed speedups in 52% of the projects. For the 52% of the projects, the configuration classes that performed the best with a median speedup of 1.59x. The best went to 2.28x, average was 1.47, and there was a slowdown of 7%. So we had the most relevant related work as electric test. The first one is electric test, which occurred in FAC 2015. The tool tracks test dependencies on global resources. The test cases are distributed across the distributed system. It follows the distributed parallelization. Now, this is complementary to our approach because our approach is targeted towards a single multi-core CPU. So the next one is particle, which occurred in Easter 2017, and this transforms C programs to GPU kernels, the OpenCL kernels for GPU level parallelization. Now again, this is domain specific, and we are yet to explore because GPUs will have no support for file system operations library calls. So we need to restrict our targeted set of applications. So the third one is TED, which is natural language processing based web test dependency detector. Now, this targets web applications that the states of the web applications that are mutated through the client server network operation. So this is again domain specific and we are yet to explore this. So to conclude, we discuss PASTE, which is a lightweight approach to parallelize execution of test suite. Broken test dependencies will be resolved by running test classes sequentially. So we had some substantial speed up. PASTE is soundy. And thank you.